Okay, so let's practice. Yeah, the first formula always works, but let's see just practice the second formula, the one that only works in the special case of the graph of a function. So let's just set up an integral representing the surface area of the graph of the function g of x comma y is equal to 6 plus sine of x plus sine of y. And we'll do this for 0 less than or equal to x less than or equal to pi, and 0 less than or equal to y less than or equal to 3 pi. Alright, so if we're going to apply the new formula here, we're going to need to compute the partial derivative of g with respect to x. So we could write dg over dx with the funny looking d's, or we can just write g sub x. And so then the derivative of this here with respect to x, only the middle term is going to give us something for differentiating with respect to x, and we're going to get cosine of x for that. We're also going to need the partial derivative of g with respect to y, and we're going to get cosine of y for that. So then the area of the graph of the function, so not the volume under the graph, but the area of the graph itself, is going to be double integral over d, the parameter domain. Right? So in this example, the parameter domain is actually that the first coordinate x should be between 0 and pi, so it's really 0 pi Cartesian product 0 3 pi. So all points of the form xy where the x coordinate comes from there and the y coordinate comes from there. Okay, of root, we're just really gonna just go ahead and copy the formula once. Let's not overwork this right now the first time around. So we have 1 plus g sub x quantity squared plus g sub y quantity squared dA, and so let's just leave some space between those integral signs. This becomes root 1 plus, and then g sub x we had over here was cosine of x. Yeah, so we have cosine x quantity squared, or cosine squared x, plus g sub y squared will be cosine squared y. And then let's convert that dA into, how about just a dx dy? Well, sure, let's do that. So then x goes from 0 to pi, and then y goes from 0 to 3 pi. Cool, there's our setup of an integral that represents that surface area. Let's go ahead and try another example. Let's so we'll just maybe copy this formula that's still new to us. How about we just copy this down here before we do a new example. And so what we'll do is let's take a look at the following question. Let's find the surface area of the graph of g of x comma y is equal to 3 plus x squared plus y squared over the disk capital D of radius 5 centered at origin 0, 0. So for our parameterization, if you want to work it out the old original way, just to connect ideas up, r of x comma y would just be the vector function x comma y comma 3 plus x squared plus y squared. And you can continue along this way using the traditional route. Okay, the parameter domain, if we were to just draw, right, should be that filled in circle here. So that filled in thing is capital D. Radius we saw was 5, and this could be in the UV plane, but if we're just using x's and y's, let's just go with the xy plane here. Okay, so then the area of the surface is the double integral. The area of the surface is equal to the double integral over the parameter domain D of root 1 plus g sub x quantity squared plus g sub y quantity squared dA, which in our example will be double integral over D of root 1 plus, and then g sub x, well, differentiate this with respect to x, and you're only going to get 2x. So 2x quantity squared plus similarly 2y quantity squared dA. Now here's the thing. We could do this integral as a dx dy integral or dy dx integral if we'd really like to set it up that way. But look at the region, yeah? What we filled in here, I mean, just based on the shape, it's circular. So it just makes sense to use integration in polar coordinates, doesn't it? So we'll leave a little bit of space here, and we'll have root 1 plus. Now let's think about it. 4x squared plus 4y squared. You can factor out the 4, and you'll have 4 times quantity x squared plus y squared, but x squared plus y squared is r squared. So 4 times r squared. There, the dA, instead of becoming dx dy, becomes r dr d theta. R, just based on the picture up here, is going to go from 0 to 5, and theta will go from 0 to 2 pi. Now, this integral can actually be worked out. We're going to leave out some of the details right now. Let's just point out that if you do u is equal to 1 plus 4r squared, things work out nicely. Yeah, that part differentiates to basically r other than some coefficients working out here. So we'll leave some details out of this process and just say that in the end you'll have 2 pi times 2/3 times 1/8 times the quantity 1 plus 4r squared, where you raised to the 3/2 power, where you need to evaluate r at 5, then at 0, and if you work this all out, in the end you ought to get pi over 6 times the quantity 101 to the 3/2 power minus a 1 still, let's see, to the 3/2 power minus a 1 still in parentheses. Certainly lots of details that you can work out towards the last part of this, but we wanted to keep things slow in the first part of the problem until we got to at least to this point right here.